Welcome, Section 4.1. We're working on Part 2 or Day 2 of our notes, and we will be looking for particular solutions today to differential equations. We are going to be able to find that value C today, assuming that we have some initial value that can get us started and pinpointed. So that is part of what we're doing today, and then we'll review a few more of those basic integration rules as well. So here we go. Yesterday when we worked on notes, the first thing we did is we took a bunch of functions that look like x to the fourth. One of them was plus 6, and I had you do the derivative of that, and you found out it was 4x cubed. And then I think we had x to the fourth minus 112, and we took the derivative of that and found out that it too had 4x cubed as its derivative. So now what we've been working on in Chapter 4 is working backwards, taking this function and trying to bring it back to the original function, so finding the antiderivative of it. So if I had this, please change your notes. Let's take it off the 2x and move it to 4x cubed, which was our result when we did our derivatives on that problem 1. This is known as a differential equation, and in college you'll hear people say they took Diffie-Q as a course, and that is a course that is centered around solving differential equations. So that's what we are going to work on today too, is solving these differential equations. Now, a differential equation is just a statement about the derivative of y with respect to x. And we found that there's a whole family of functions that have the same derivative. We found out that there are many things that have this family of, well, 4x to the third is an example. This antiderivative is known as a general solution. When I do the antiderivative of this, I'm going to get a general solution that had started with x to the fourth, and then we would have some plus c. That's going to be known to us as a general solution. Our goal, though, today is going to be solving for y with respect to x and get a specific solution for the constant of integration. So how will we be able to figure out what c is? Well, we'll be able to figure it out if we're given some initial condition, and that means given some point that we know that our function maybe passes through. Maybe it passes through the point 1, 3. That's going to help us very much to get into this specific solution. So differential equations, a little word on this. I can multiply both sides by dx here, in a sense, and bring it over to the other side. So I end up with this equation dy equals 4x cubed dx. And if I want to solve this differential equation, I simply integrate both sides. And as I integrate both sides, the integral of dy becomes y equals. The integral of this will become x to the fourth raised to power, I had that 4 multiplier in front, and then divide by the new power and plus c, right? That's been our procedure that we learned yesterday. So here's my general statement. My general solution would be y equals x to the fourth plus c, known as a general solution. When we have that c for the constant, that's what it's referred to. All right, so number 6 says solve this differential equation given these specific conditions. Well, this is my initial or my specific condition. So I'm just going to call this my initial condition. When I plug in 2, I get out 5. And a way to interpret that f of 2 equals 5, right? So I know my curve will pass through this point. Take a note of that. It passes through this particular point. Over on the left here, when I see f prime of x, we know we also could rewrite this as dy dx equals 2x minus 1. They mean the same thing. A derivative, a derivative. So the derivative is equal to 2x minus 1 is what this would read. Let's bring the dx over to the other side, multiply both sides by a dx, and I would have this. I want to solve this differential equation, so I'm going to integrate both sides. So go ahead and write your integral symbols. Integrating the left becomes just a nice y value. Integrating on the right, I'd have 2x. Raise it up by a power, so I'd have 1 plus 1 gives me 2. Divide by that new power, so divide by 2. Minus 1, I've got a constant. I need to bring in x then, plus c. Don't forget your general solution. This right here, what we are sitting with, would be known as the general solution to our differential equation. And we can simplify one more step here. So y equals x squared minus x plus c. I want to take us now into the specific solution. And the steps to do that is we are now going to substitute that known point that our curve passes through. So now substitute in that value 2, 5. That's going to look like my y value of 5 equals something squared minus something plus c. My somethings was this x value of 2. We want to pass through this point 2, 5. So I know this has to be on my curve, so plug it in. Evaluate, and we get 5 equals 4 minus 2 plus c. See how we're going to be able to solve and find c. Bring the 2 over, and it appears that our c is a 3. Excellent. Final step is to rewrite this equation now with c. Rewrite to give the specific solution. And that's going to be really easy. I'm going to look back to this point here. I get y equals x squared minus x plus, I have found out that my specific solution was 3. My specific c value was 3. This is the curve that will pass through 2, 5, guaranteed. Want to try another? A lovely trig one. Let's do a trig function. If it helps you to identify the point, don't be afraid to just jot that down in ordered pair style. I think sometimes that helps. When x goes in, we get out this y value. So f prime of x could be rewritten as dy dx is equal to 2 cosine x. Swing the dx over to the other side by multiplication. Integrate both sides. And I purposely put the 2 on the outside there because I can think of just now integrating cosine. Any multiplier can be brought out there, can it? So the integral of cosine. Well, the derivative of sine is cosine, so that means working backwards, the antiderivative of cosine must be sine. So it's sine x, and then plus a constant. Don't forget your constant. I want to find my specific solution, so let's go and find c value. Substitute in that point, pi over 2, comma negative 3. So I get negative 3 is equal to 2 sine of pi over 2 plus some c. I substituted in my x and my y. Okay, let's evaluate and find c. Solve it. Negative 3 equals 2 times 1 plus c, because the sine of pi over 2 is 1. That means I have negative 3 equals 2 plus c, therefore c is equal to negative 5. Hang on to that value, because now we're going to go and rewrite the specific solution. The specific solution. And that is going to look like, well, where was our general? This was our general. Maybe you want to write that on the outside of this. This was our general solution because it had just the c. So I'm going to start up with my general solution. Y equals 2 sine x plus we found out c was -5, so 2 sine x minus 5. And we know that this particular curve passes through the point pi over 2, -3. If you use your graphing calculator to do it, you'll find that to be the case. If you want, let me put the shade on this for a moment. I went ahead and did this. I don't know if you need more practice, but I would encourage you to give it a try on your own. So go ahead and do this problem, hit pause, and when you come back, there's your solution. Same thing for problem D. I have done the work. I want you to give it a try and see if you come up with the same thing I did. So go ahead and hit pause and work this problem out. The solution is down here in the right-hand corner. See if that matches yours. Okay, and then I just wanted to do a little bit about integrating with different variables. You can integrate with respect to x, t, theta, all of those. So this particular one, I noticed that they've put in the variable t. And this differential out here at the end tells me that I'm doing my integral with respect to t. So if I integrate this particular one, the integral of 1 will be t minus. Okay, so what gives us cosecant cotan? If I took the derivative of cosecant t, it would give me negative cosecant t cotan t, which that's a complete match, isn't it? So the antiderivative, working from the right side back to the left side, the antiderivative over here will be cosecant t plus some value c. On this one, notice that you're working in thetas, and it says differentiate or integrate with respect to theta. So I'll just have thetas, theta to the third divided by 3 plus secant squared. Whose derivative gives you secant squared? The answer to that is tangent, of course. Derivative of tangent gives me secant squared theta. So working backwards means that my solution up here would have been a tangent theta plus c. Now, just a quick word about antiderivatives and their particular, or sometimes they're referred to as the specific solutions. We've done some of those equations where we found c. Here's a different way of looking at it. In problems 47 and 48, I believe you have to do 47 in your homework, you want to find the equation for y given the derivative and an indicated point. So what they're giving me over here on this left side are many, many curves. You can see that. They're all parabolas. Some pass through different points, but they still have the same basic shape. So there are many solutions here to a general integral problem, and that's what this is trying to display. Here is your specific solution. We'd have passing through the point 3, 2, and then here's our differential equation that we want to solve. So it's just like we had done on problems A and B. Let's break up the dy dx. So dy equals 2x minus 2. Notice I passed that 2 through, and then we'd have our dx over on the right hand side. Let's integrate to get our general solution. So I'll have the integral is y equals 2x squared divided by 2 minus 2x. All I did was up by a power. I had 1, so I added 1 to it. That produced the 2, and divide by 2. The constant 2 will get x added to it, because remember this was like x to the 0, so 0 plus 1 gives me a power of 1. And then don't forget to add your constant. Now, here's my specific point that I want the black dark curve to be written regarding this general solution. So we're going to take this general solution and try to move it into a specific solution that will look like or graph out that black darkened curve. And I'm going to put in 2 for my y, and then I'm going to put in 3 for my x. So I have 3 squared minus 2 times 3 plus c, and that allows us to find c. We'll have 9 minus 6 plus c. C plus 3 equals 2, subtract 3, and we're at negative 1 equals c. Now for just rewriting it, we know c, so we pick up where we had this general solution, which was kind of messy up here. That was my general solution. The specific one going through the 0.32 will be x squared minus 2x minus 1, picking up our c value that we solved for. So really no different than what we did in problems A and B. It's just we have that graph there to help us out. And that brings me to this page here. These are called slope fields. I doubt that you've ever seen anything that looks like this, but what's going on in this picture is you are getting slopes at every particular x value. When I'm looking here at x equals 0, I see that I've got a positive slope. Perhaps the slope is a value of 1, you know, and then it's getting a little softer when maybe this is an x equals 1/2 value. Looks like it's a little less steep. Maybe it's a slope of 1/2. And then it's even getting less steep when x is 1. This is actually a 0 slope when x is equal to 2. Sorry, maybe it's more like x equals 1.5 there. So you can see all kinds of slopes happening. It's called a slope field. It is a way of representing the derivative, because when we write the equation of when we solve the derivative, we get all kinds of slopes at particular x values. So this field consists of line segments with slopes given by the differential equation dy dx equals cosine x, which gives the slopes of the tangent lines to the original functions. So what you're seeing there are those slopes that are coming off the equation of the tangent line. A slope field is useful because it can be created without solving the differential equation. This differential equation is what is displayed there. Anytime I put in a value of x, cosine of 0 is 1, right? Cosine of 0 equals 1. Well, that is the dy dx. That is the slope. And notice how we kind of said that looks like about a slope of 1. Well, indeed it is. And if I changed up and did cosine of pi, let's say, cosine of pi, well, that's going to be close to a -1 slope. And if I look out here, pi, this is 3, so 3.14, you can kind of see how there's negative slopes going on over there. So this differential equation, which really is the slopes equation, is displayed by the slope field. What I want you to do is to solve and tell me what the original function was. We want to find the antiderivative. With slope fields, I can give you an idea of what that curve looks like. Just take your pencil and sketch through. Follow the general flow of that function. And maybe I should even continue to come down here a little bit further. This would be my specific solution, right? This would be the specific solution curve. It's passing through this very specific point, which was 0, 4. So we found the one curve that went through that. Are there other curves that mimic this? Absolutely. The only difference for these curves is that they have a different c value, a different constant. And that constant raises or lowers this general family of graphs. So the way to do this is the same that we've been doing it all along today. We will take this dy dx and separate it up, multiply by dx on each side, and that gives us that. Let's go and integrate this to find the antiderivative. Therefore, y equals the function that has a derivative that is cosine is sine. Check it out in your mind. Derivative of sine is cosine. So we have found the correct antiderivative, and then I'd have plus c. If I looked at 0, 0 here, does that look like a sine wave? Indeed it does. At 0, sine should be 0, shouldn't it? Now let's find c for our specific solution curve, and that is the one I'm going to leave revealed here. We want to find the equation for that. Plug in our initial condition. 4 equals sine of 0 plus some c. That will make c plus 0 equals 4. Oh, in other words, c is 4. Take now, move from the general solution. It's good that I'm using these terms over and over, but they become important because when asked to find the general solution, you'll know you should have a C in your answer. When asked to find a specific solution, you'll know you should have a value for C to substitute in there. And there is our specific solution, or another word is a particular solution for this curve. And this looks about right, doesn't it? I am up by 4. A sine wave starts lower and moves up right away. So I started low and went up. There we go. I think I'll pass on this one. We can do that in class. Here will be the homework for day 2. So there it is.